Hello folks, my name is Evgeny Ray and welcome to the Frontend Engineer channel. Today we're going to look at the interesting piece of technology that everybody uses, but actually not everybody know how it actually works. So today's topic is HTTP protocol. So I've decided to split this discussion into the two videos. The first video will give you the great overview of the HTTP protocol in general, how it positions itself into the architecture of the web things, and we're gonna look at the deficiencies of the early versions of the protocol, what are performance tricks that engineers use to improve the performance, and spoiler alert, the engineer still uses these techniques, but they're actually outdated and not relevant anymore, and not recommended. So yeah, it's gonna be pretty interesting discussion. So if during the video you feel like you still have some questions and you want to dive deeper into the topic, I highly recommend reading this book. So, as usual, before we start, please subscribe to the channel, hit the like button, and let's go. So, before we jump into the HTTP protocol, let's overview how the web actually works. Suppose that you want to fire up a browser request and go to the frontend-engineer.io website. So, what happens? The browser requests the real address of the frontend-engineer.io from a domain name system, which is also called DNS server. The DNS server translates the human-friendly name to the machine-friendly IP address. The web browser asks your computer to open the Transmission Control Protocol, or TCP connection over the IP address on the standard web port 80 if the connection is HTTP, or over the standard secure web port, which is 443, when the connection go through the HTTPS. When the browser has a connection to the web server, it can start asking for the website. This step is where HTTP comes in. If HTTPS is used, some extra steps are required to set up encryption, but we will skip this part to keep the things simple. Initial page gets rendered, which is in our case index.html. Page rendering begins, and while the browser parsing the page, it can encounter that it needs to load some additional resources, like JavaScript files, CSS, images, and so on. So we can only render the page when all resources are loaded. This is also called critical resources. Once everything is loaded, the page getting rendered. After the initial rendering complete, we can also request some. We can do also some background requests, like with the onload event or some AJAX requests for additional resources. This schema repeats each time you request a new web page, and we'll use this model throughout the video. With that in mind, let's jump to the HTTP. So what is the HTTP? HTTP stands for Hypertext Transfer Protocol, and as the name suggests, HTTP was initially intended to transfer hypertext documents, basically the documents that contain links to other documents. And the first version didn't support anything but these documents. However, the web evolved pretty fast, and developers realized that other types of resources can be transferred, such as images, script files, binary data, and etc. HTTP requires the network connection and work over TCP/IP, which represents the physical connection, such as Ethernet cable or Wi-Fi. OSI model is the conceptual model often used to describe this layered approach, and the model itself consists of the 7 layers. So the first layer is the application layer. Many web applications are built on top of HTTP, so the application layer, for example, refers more to the networking layers than to JavaScript application itself. HTTP is the request and response protocol. The web browser makes a request using the HTTP syntax to the web server, which represents the message containing the requested resource. So the second layer is the presentation layer, and it's used to describe the response that can contain multiple formats of the files, such as JavaScript files, CSS, or PNG, and so on. This layer determines what formats are supported and can be transferred and presented. The session layer is the third layer, and it provides the security of the connection. This layer kicks in when we work with HTTPS, as the encryption is set up for the connection. The fourth layer is the transport layer, and it represents the protocol we are using to transfer our data. And as we know, the HTTP works over TCP, and the TCP works over the IP, which is represent Internet Protocol. The the fifth layer is the network layer. So it represents the Internet Protocol itself. The data link and the physical layers represent how we transfer our physical signal to our device, and this is done via cable or the Wi-Fi. We'll skip the last three layers, which is network, data link, and physical, as they're not relevant for our discussion of HTTP. Now we know how the HTTP positions itself into the high-level architecture of the web, and I think it's really helpful for us to dive deep into the evolution of the protocol to understand how it evolved with the increasing needs of the web world. The first version of the protocol was 0.9, so the HTTP as a protocol started super simple. The first and the only possible command was the GET request, and the syntax looked like that. So as you can see, it's a simple GET request with a single param that represents the path to the page. And the key features of this protocol was that the response represented a stream of ASCII characters, and there is no error state that will allow to determine if response successful or finished with an error. This was only introduced in the next versions of the protocol. All requests are idempotent, meaning that all requests are not mutable and you'll always get the same response for the same request. And of course, there was no header support. With the time, the protocol was getting more complex and HTTP 1.0 was introduced. So HTTP 1.0 was a major release and introduced many new features like additional request method, head and post. Head allows the client to fetch all meta information for a resource without downloading the resource itself. For instance, browser can get the image size ahead of time and then reserve the space on the page in advance. The post allows the client to send the data to the server and allows to send the content as a part of a HTTP request, also known as a request body. HTTP version field allows to specify the version of protocol to use for communication. So for backward compatibility, it was set to 0.9 for quite a while. At the moment, like most of the clients, has it as 1.1 and as a default. HTTP headers were also introduced in this version of the protocol, and they can be sent with the request and the response. The free response code, this code also enabled many things like requests, conditional requests, error statuses, and so on. So 404 is one of the best known code for the case when resource is not found on the server. So with the current changes, the syntax of HTTP protocol advanced to the following state. The HTTP version is provided as additional param, and the headers are set as the key value map. A more real-world example would look like with many additional headers specified in the request. Here you can see the example here. We have accept header, accept encoding that represents what type of the encoding the client supports. Accept language represents what type of language the browser is supporting. Yep, and basically this is one of the core features of the HTTP1 protocol. The next version, which is still used by many servers, is HTTP 1.1, and let's talk about it. So HTTP 1.1 was more like a refined version of HTTP 1.0. Most of the features introduced in this protocol were based on the HTTP headers, which themselves were introduced in HTTP 1.0, meaning that the fundamental structure of HTTP didn't change between these two versions, except two notable changes: mandatory headers and their persistent connections. So let's quickly explore these core features. So the first core feature was a mandatory host header. The URL provided with HTTP request lines isn't absolute URL, but it's relative URL. When HTTP was created, it was assumed that the web server would host only one website. Therefore, the host part of the URL was obvious, because the user had to be connected to that server before making any HTTP requests. Nowadays, many web servers host several sites on the same server, a situation known also as virtual hosting. So it's important to tell the server which site you want to access, as well as the relative URL that you accessing on this website. This feature was implemented by adding the host header to the request. And here is a simple example of this host header. If we look at the additional example, a request to the main page with a different host param should result to a different website being requested. This header was optional in HTTP 1.0, but HTTP 1.1 made it mandatory. The following request is technically badly formed, so it's because HTTP 1.1 specifies that the host header is required. So let's jump to the next feature, which is called persistent connections, or keep alive. So initially, HTTP was a single request and response protocol. The client opens the connection, requests a resource, gets the response, and then connection is closed. Displaying a single page requires several HTTP resources, so closing the connection and reopening it again was causing unnecessary delays. The problem was resolved with a new connection HTTP header that could be sent with HTTP 1.1 request. So by specifying the value keep alive in this header, the client is asking the server to keep the connection open to allow the sending additional requests. The server would respond as usual, but if it supported persistent connection, it will include the connection keep alive header in the response. The response tells the client that it can send another request on the same connection as soon as the response is completed, so the server doesn't have to close the connection to the client only to reopen it. HTTP 1.1 not only added the persistent connection process to the documented standard, but also went one step further and changed it to the default. Any HTTP 1.1 connection could be assumed that to be using persistent connection even without presence of the connection keep alive header in the response. If for some reason the server did want to close the connection, it had to explicitly include the connection close HTTP header in the response. So other new features that were introduced HTTP 1.1 were like new methods, put options, and less use connect and trace and delete. Beta caching methods. These methods allow the server to instruct the client to store the resource, such as CSS file, in the browser cache, so it could be used later if required. This is also known as the caching header that should be configured on the server. HTTP cookies to allow HTTP to move from being kind of stateless protocol, new status codes, proxy and authentication support. So, and knowing the evolution of the protocol to this state, I think we're ready to discuss the prerequisites of HTTP 2. Why the committee had to create the new version of HTTP 2 that would solve many problems of HTTP 1. So let's look at the HTTP archive report to understand how the website payload size and an average number of requests changed over the time. As you can see, the average websites grew from 100 kilobyte to 5 megabyte. The average request number is about 70 requests per website. Essentially, website became more complex, with multiple frameworks, libraries, and dependencies needed to display their content correctly. Web pages started out as static pages, but as the web became more interactive and the pages started to make a lot of calls from the client side, JavaScript, the HTTP protocol wasn't designed with a huge increase in resources in mind. And here we come into the discussion of fundamental problems of HTTP 1.1 protocol. So the first fundamental problem of HTTP 1 protocol is no parallel resource loading. So as we remember, the HTTP started as a simple request and response protocol. Back in the old days, web pages were simple HTMLs with no additional resource to load. If we look at the loading of the modern website through the HTTP 1.1 lenses, you will see the fundamental problem here. Let's assume that the browser makes a request to some website. We request some HTML page, the server responds with a requested page. Browser starts to render web page and sequentially load every resource that it sees in HTML, like JS and CSS files. The page is rendered only when all critical resources in the HTML page are fully loaded. After rendering is completed, the browser will be executing some additional requests made by a sync script. As you noticed, until all resources are loaded, the web page is not displayed. This creates a significant latency and time to render and leads to a huge delay for the user and spending like 80% of the time waiting for the messages to travel across the internet. If the website contains like 50 plus resources, the impact is critical. Although some workarounds were introduced to fix this problem, and we'll discuss it in a few moments, this fundamental problem was one of the largest prerequisites for introducing HTTP 2.0. The next annoying problem is the potential large header size and compression. Although the bodies of HTTP messages can contain binary data, The request and the header themselves must still be in text. The text format is great for humans, but it's not optimal for machines. Text format makes HTTP messages larger than they need to be, due to encoding data inefficiently and repeating the headers. The use of HTTP headers has grown, which leads to a lot of repetition, and with the security HTTP headers such as content security policy, producing extremely large HTTP headers. With many websites being made up of 100 and more requests, large HTTP headers can add like hundreds of kilobytes of data transferred, and the issue is becoming more critical, especially in the countries with high cost of the traffic. Despite issues sounding like pretty bad, some workarounds were introduced that help to decrease the impact of protocol limitations. So it's time for us to discuss HTTP 1.1 performance workarounds. As a front-end engineer, most of you probably use or still use these tricks to optimize the performance. Anyway, I think it's still helpful to go through them because many websites still have not migrated from HTTP 1.1, and in your project, you might have used them. And some of the advices do contradict with HTTP 2 paradigm, so be careful using them in the modern app scenarios. So one of the easiest way to get around the blocking issue of HTTP 1.1 is to open more connections, allowing parallelization to have multiple HTTP requests on the go. Most browsers open 6 connections per domain, although even 6 parallel connections are not enough to fix the issue, and engineers found a follow-up workaround. So the second technique is called domain sharding. We know that there is a hard limit of 6 connections per domain. To increase the limit of 6 even further, we can serve the static assets such as images, CSS, and JavaScript from subdomains, allowing web browsers to open a further 6 connections for each new domain. Often these shared domains are hosted on the same server, sharing the same resources but using different domain names fools the browser into the thinking that the server is separate. Using multiple HTTP connections sounds like a simple fix to improve the performance, but it's not without downsides. The additional overheads for both the client and the server when multiple HTTP connections are used. Starting a TCP connection takes time, and maintaining the connection requires extra memory and processing costs. The main issue with the multiple HTTP connection, however, is significant inefficiencies with the underlying TCP protocol. As we know, TCP is a guaranteed protocol that sends packets with a unique sequence number and requests any packets that got lost on the way by checking for missing sequence numbers. TCP requires a three-way handshake to set up. And let's look at the picture to understand the issue more. The client sends the synchronous message that tells the server the sequence number it should expect in all future TCP packets from the requests based on. The server acknowledges the sequence number from the client and sends its own synchronization request, telling the client what sequence number it will use for its messages. Both messages are combined into the single sync and acknowledge message. Finally, the client acknowledges the server sequence number with acknowledge message. This process adds 3 network trips, or 1.5 round trips, before you send a single HTTP request. And this is one of the most critical downsides, especially for mobile users, as the message have to travel across multiple cell phone towers along the way, resulting to the high latency. So the second downside of this approach is bandwidth exhausting. Even without any issues with TCP setup and slow start, using the multiple independent connection can result in bandwidth issues. If all the bandwidth is used, for example, the result can be like TCP timeouts or retransmissions on other connections. Keep in mind that unlike HTTP 2, there is no concept of prioritization between the traffic on those independent connections. So HTTP 1.1 is not able to use bandwidth efficiently. To conclude our discussion on the first workaround, multiple TCP connections aren't a great solution to the problems of HTTP 1.1, though they can improve the performance when there is no better solution available, but you need to keep in mind that this approach adds infrastructure and maintenance cost. Each connection consumes a great chunk of server and the client resources. Optimization requires specific domain knowledge and more expensive specialists, and many other side effects. For example, one of them is higher battery consumption on mobile devices. With that in mind, let's explore the second workaround that results into many modern tools being created like Webpack and data bundles. So the second workaround is to make fewer requests. This seemed like an obvious approach, and in order to achieve that we can use the following strategies. The first one is caching. Browser can cache the resources from the server and reuse them later, providing the necessary caching headers as supplied. The second one is image bundling. This technique is still actively used and also known as a spriting, so you can pack all your icons into one large file and it will be loaded in one go. But you can later use JS and CSS to extract the icon that you need. This technique reduces the number of trips required to the server and can help with the problem when requests getting queued, because website has lots of images to load. For instance, normal website use about hundreds of images. So this technique definitely will help to load these images in one go. So the third technique is CSS and JS bundling. This is one of the reasons why Webpack and data bundles were introduced. Basically, you can merge all the critical resources into one file and serve them as a bundle. This technique also involves compressing and minimizing the file. The fourth technique is inlining the critical resources. CSS styles can be served together with HTML by putting all the critical styles that are required for the page into the style tag served with HTML. So the downsides of all these approaches is that there is increased traffic and file sizes. Clients with bad internet connection may suffer the significant latency time. Not all code is used during runtime. Some parts of the website or images may never be accessed, leading to serving unnecessary payloads. Caching. The code of the website tends to change, and with the bundling approach, the bundle will always has to be re-downloaded in case of any small changes. So because it produces, each time you do the changes, it produces a new bundle. So caching strategy here can be really tricky to set up. And as you can see, industry found the performance workarounds, and these workarounds, however, take time, money, and understanding to implement and to maintain. And going forward, they add their own performance problems. Developers aren't cheap, and having them spend time working around an efficient protocol is necessary but costly, not to mention that many sites that don't realize the impact of the poor performance on the traffic. So multiple studies show that a slower website lead to the abandonment and loss of visitor and as a result, sales. So to fix these problems, HTTP2 was introduced. So that's it for today's discussion. And in the next video, we're gonna discuss how the HTTP 2.0 is designed and why it's so drastically different, how the multiplexing and by-stream prioritization help to resolve many issues that we discussed today. So if you're looking forward for the next video, please subscribe to the channel, hit the like button, and also post what you think in the comments below. But for now, bye and see you soon.